this video, we're going to look at how Q equals mc delta T can be used to find a measurement that we call delta H. Delta H is a measurement of the change in energy in a chemical reaction that occurs when reactants are converted to products. If delta H occurs in the products, that means that this reaction produces energy, which is then released into the environment as heat. If delta H occurs in the reactants, that means that this reaction absorbs energy from this environment and requires that energy in order for the reaction to happen at all. In either case, we need to do the chemical reaction to measure what delta H is, which means that we need a special tool, which we call a calorimeter, in order to measure how much energy is produced or consumed by the reaction. The way a calorimeter works is that all necessary reactants are placed in a sealed reaction chamber called a bomb. Once the reactants are sealed within the bomb, a certain amount of energy is added to the bomb and creates a small explosion, hence the name bomb, that causes the reaction to start. This energy, which is supplied by a spark plug, is what we call the activation energy, or simply the energy required for a reaction to start. At this point, one of two things can happen. If we assume that this reaction generates heat, which means that the reaction produces energy, that energy is going to be released from the bomb and go into the water. Now, when the heat from the reaction is released into the surrounding water, it causes the water temperature to increase because, again, if the reaction generates heat, that heat is going to go into the water and cause the water molecules to move faster, which we would perceive as a hotter temperature. But not all reactions produce energy. What would we observe if the reaction consumes energy? Well, in this case, the opposite would happen. In this case, if the reaction in the bomb requires energy to happen, the reaction is going to absorb heat from the water through the walls of the bomb and into the reaction in order to power the reaction. In this case, because we're taking heat out of the water and putting it into the reaction, that will cause the water temperature to decrease because there is less heat in there than before. Now, if we want to measure the movement of heat, we see that the heat has to cross through the walls of the bomb first before it can enter the surrounding water, which means that our formula for heat transfer needs to reflect that. So we can't just consider the specific heat capacity of the bomb. We also need to consider the amount of heat that the bomb can absorb per degree Kelvin that is increased in order to look at the total amount of heat transferred. So our formula would reflect that, where we have the specific heat capacity of the bomb multiplied by the change in temperature. Because the mass of the bomb is constant, we don't usually consider that. Next, the rest of our formula is exactly as you'd expect. Because the heat is eventually transferred to water, we would need the mass of water multiplied by water's specific heat capacity, 4.184 joules per gram per degree Kelvin on the temperature change, multiplied by whatever that temperature change is. This first example here is a fairly standard calorimetry question, and all of the information is given here. If we want to start with the bomb half, we see that our specific heat capacity of the bomb is 837 joules per Kelvin. Again, notice the mass is not given because the mass is built into this, and the mass of the bomb obviously doesn't change. We see the temperature change is listed right here, and we can just eyeball this calculation here. We know that delta T is going to be 5.80 degrees Celsius, and again, because we're measuring a temperature change and each degree Celsius is the same as a degree Kelvin, these are the same measurement here, so we can just multiply our specific heat capacity of the bomb by 5.80 Kelvin, and there's the first half of our equation. Next, we need to consider the mass of water, which is given in scientific notation, 1,500 grams of water, which we then multiply by our specific heat capacity, 4.184 joules per gram of water per degree Kelvin of the temperature change. So we see that grams cancel, and we simply need to add in our change in temperature, which we've already calculated. And if we put this into our calculator, we should get the total heat transfer that occurs in this reaction. Assuming that your arithmetic is correct, if we do not round this, you should get 55.4 joules. Now, we see from our measurements that our measurements all give us 3 significant digits, so we can round this to 41,300 joules. We can see for our second calculation, though, that we will need this measurement in kilojoules. So let's make one quick unit conversion and divide this number by 1,000 in order to give us approximately 41.3 kilojoules. Now, typically when we are calculating delta H, remember that delta H refers to an energy change that occurs in a chemical reaction. So typically, delta H is measured in energy units per mole. So here, we're not given the amount of moles of sucrose, but that's an easy calculation that we can do. So if we want to set this up so that we can do this in one line, we know that our final unit is going to be in kilojoules per mole. So if we put our unrounded measurement here to avoid accuracy errors, 41.2554 kilojoules, and we're going to divide that by the number of moles of sucrose, which is 250 grams of C12H22O11. And of course, we need to divide this by the molar mass of sucrose in order to find out what this number is. So if you go to your periodic table, or if you just remember what the molar mass of carbon, oxygen, and hydrogen are, molar mass of carbon, 12.01 times 12, comes to 144.12. Molar mass of hydrogen is 1.01 times 22 is a very convenient 22.22. Molar mass of oxygen is 16 times 11 comes to exactly 176. And if you check my arithmetic, you should get 342.34 grams per mole. So we can divide our mass of sucrose by the molar mass of sucrose here in order to find the number of moles. When you put this into your calculator, you should find that this number comes to, with 3 significant digits, 565 or 5.650 times 10 to the 3 kilojoules per mole, or 5,650 kilojoules per mole. Again, recognizing 3 significant digits, we can get rid of the 0 and we can just say 5.65 times 10 to the 3 kilojoules per mole. So now that we have a method of calculating how much energy can be produced by the reaction, the next series of videos will cover a few of the definitions of what terms actually mean in terms of when a reaction produces energy, when it consumes energy, and the energy that is required in order to start chemical reactions.